Hi, my name is Alexis McKay, and this is my presentation on shear and moment diagrams for BCN 2405, or statics. So first, to start off, what is a shear and moment diagram? So, shear and moment diagrams are a graphical representation of the internal shear force and bending moment along a beam. A moment diagram in particular is where the horizontal reference axis represents distance along the beam, and the ordinates represent bending moment at the section that was selected. So you guys can see that I included figure 7.5 from the textbook. This includes load, shear, and moment, all of the diagrams. So it has the moment diagram right here and the shear diagram right here. So a shear diagram is a graph where the horizontal reference axis represents the distance along the beam length, and the vertical measurements from the reference axis represents a transverse shear at the beam section selected. So you can see that right here, V and M, they do both look different. It's because they are different. One is a moment right here, and then one is a shear diagram, which is right here. The next slide that we have is sign convention. Sign convention is extremely important to be able to remember. So basically, you want to make sure that you use the proper sign convention for shear and moment diagrams. This is so important only because if someone else is reading or interpreting the diagram, you want to make sure that they're able to read it and interpret it without any issues, with no confusion, and it's very, very clear and easy to understand. So, the shear at a section is positive if the left portion of the beam is raised more than the right portion of the beam. However, if the beam is lower on the left-hand side, then the sign convention will change and become negative. I put in this example, figure 6.7 from the textbook, 7.6, I'm so sorry. This one right here. So basically, it shows that this left-hand beam, it's raised slightly more than the one on the right-hand side, and because of that, the sign convention is positive. But if you look at this one, where the left section of the beam is lowered and the right section of the beam is actually higher, because the beam is changing and which side of the beam is raised is changing, it's going to be negative. And the sign convention is going to change. So it's very important to make sure that you add that sign convention, especially with this. And then for this one, figure 7.7, it basically just shows that if the compression is on the top of the beam, then the moment, the sign convention for moment will be positive. However, if the tension is on the top of the beam and the compression comes from underneath the beam, then it's going to be negative. So the sign convention will change depending on where the tension and compression are, especially in terms of this figure right here, 7.7. The next slide that we have is the equilibrium method for shear and moment diagrams. So this is one of the more simple methods used to determine the shear and moment diagrams. Unless the load is distributed uniformly or varies according to a known equation along the beam, no single expression can determine the shear or moment. So what this means is that because, unless the load is distributed evenly, or we have a known equation, you can't just make up an equation that will apply. So, especially not for the whole length of the beam. To get the entire length of the beam, you're going to have to split it into different intervals. So, the best way to construct the diagram is to draw the free body diagram of the entire beam and then do the moment and shear diagram directly below the free body diagram. First, it's important to select an origin point, and different origin points can be used for different intervals. A completed shear and moment diagram should show values of shear and moment at each section where it is maximum positive or maximum negative. Sections where the shear or moment is 0 should also be identified in the diagram. This is example problem 7.2 from the textbook. You can see over here, right here, that the first step that I had to do was to find the summation force of y, which would be By, which ends up being 20K. I then had to find Mb, which ended up being 200K times feet. And for the shear and moment calculations, they're right here. So VA is 0K, MA is 0K feet, and then the VB for the left part of the beam is 20K, and the VB for the right part of the beam is 0. And then the MB is 200 again. So right here, you can see that this is the moment diagram right here, where it bends and it has a curve, whereas the shear force diagram is straight and cuts directly through. But you can see that they are fairly similar. The final shear and bending forces right here, we get that from these numbers right here. So whenever it comes to doing the diagram, the best way to do it is to make sure that you have the free body diagram, your shear force diagram directly below it, and then your bending moment diagram directly below the shear force diagram.